I'm recording this video to just think out loud about calculus. I'm taking this as one of the first problems from an old calculus book that I have, Modern Calculus with Analytical Geometry, Volume 1 by A.W. Goodman. And on page 7, we just read through all of the things that talked about mastery of sets and subsets and complex numbers. And now we're on the area and it's thinking about proofs. And one of the ways that we think about proofs is to state which are identities, which means every element that could be plugged in for x would be true, and to give you an equation like sine squared x, or sine x squared is the better way to read it, and cosine x equals 1. So I'm looking for every line. If this indeed is true for all portions of the equation, my y in that formula should always end up being 1. And but even if it doesn't, there will be a number that appears, and that number will tell me whether this particular formula or function is indeed true, or which or if it's conditional or not. If it's conditional, it only has 1 every now and then, or once in some cases. So let's look at this particular equation. So one of the things I want to do initially is probably to tell you actually how I made that sign up there. In order to do that inside Excel, you have to basically go to Insert, click on Symbol, and this is how you add a power sign or a lot of mathematical signs to your program. And it's found in the Latin supplement, which is in my particular version of Excel. It's the second one down, and it shows the power of 2. So if you click on that and insert it here, and it shows you the hex, the Unicode hex number, which is this here, 00B2. All of those kind of work. You can actually type it in Word and paste it in here too. Hit it, insert, and it will actually appear within the cell. So hopefully that helps. It took me a while to get that in there. I guess to help establish what this is, you can see the initial plot, and it's going from 0 up, and sine square usually appears between 0 and 1. I know that I've done this before, but what I want to do is show you what a sine wave looks like, and that's what it's going to actually paint on the chart, is the wave, which means a circle laid out over time, if you will. And I've actually calculated pi in tenths, and pi is the 16th letter of the Greek alphabet, but in calculus it represents a ratio between the circumference and the diameter, and it's an irrational number, if you will. So they use a symbol to represent that number, and that number, when you try to show it in a decimal form, is a non-repeating decimal. And people have been known to go in the Guinness Book of Records repeating that number over long spans of digits. So I took the power sign off, and I'm just going to copy this through the first, how about this, the first quarter, or 1/4 the way around the circle. So you see how it goes up and touches here. Now I'm going to copy that over the next quarter of the circle. I think I can do that by that. Yep, that's it. So that's halfway around the circle. Take special note when I go 3/4 the way around the circle, it's showing you that it dips down below 0, and if it was a circle, it's actually turning the corner and going back around. If you're a track star, This is the third quarter of the loop around the track, and this is going to the finish line, so it goes back to 0. And so this is a sine wave, if you will, but not a sine square, but a sine wave. So let's go ahead and finish off here. How many loops I got? I have 3 loops. 1, 2, 3. Okay, that's what that looks like. Now I'm going to show you what a sine squared or sine x squared loop might look like using this ratio to fill out circle. I think this will do it. Yep, I got the power sign back in, so I'm gonna copy it down across all of it, and you'll notice how this changes. It'll actually show everything between 0 and 0.5. Let's see if that works. It does. Here's 0 and 1, excuse me, between 0 and 1. And this is blue, and notice going forward, all the sine numbers will be blue on this table. This table was an easy make, so if you're trying to repeat this at home, you just go here to where it says Insert, click on Scatter in your table area, and Scatter, I use this one here, and I could change it to this one, and I'll do that towards the end. This one actually shows straight lines between the points. This one shows curved lines between the points. It's a subtle difference, but as I'll show you at the end, and I think you'll see the difference that it makes. But I'll use the straight lines right now, and I'll clear out the sine squared information, except for the first point. Point 0 is right here at 0. So you can notice how that changes around. Now I'm going to do cosine x. And cosine x is basically a ratio of an angle. When you think of, if you were thinking about triangles as in trigonometry, it's basically the length of the hypotenuse. Okay? And it's a ratio between that length and the length of the adjacent side. So, look, I think you find all kind. Google that up. You can see all kind of pictures of the representation of that. So, and I didn't do it step by step, and maybe that would help. Let's see. Let me do that. Just like I did the first one. Show you just the first quarter turnaround. So the first quarter looks like this, from 1 down to 0, and it's red, and that's my cosine. Let's do the next turn. Down to pi. So that was pi over 2, if you will, or half pi. And this is pi. That's halfway around. And this is a little bit more than 3/4 around. That is 3/4 around, the third leg of the full time around the track. And then this one here is 2 pi. So that shows a complete loop for the cosine. So from 1 to -1 up to 1. And wherever it touches here, that would be your quarter and your 3/4 time around. And as I said, I broke it into tenths. So this is 1/10, or excuse me, this is the first point. 0, this is 1/10 plus another tenth, plus another tenth, another tenth, another tenth. So it takes 5 of these to get to here, and 5 more to get to here, and 5 more to get to here, 5 more to get here. Now let me show you the whole thing, as I already did, and the lines that link it all. So this is 3 cycles. Said, done. It's a good visual, helps explain how I can determine if it's equal to 1 in all circumstances. I think right now you can see it's not always equal to 1. If it was, it'd be a straight line somewhere for both of these, or maybe it is indeed an intersection. So I'll show you what I mean by that. When you add, so this shows the first point where sine x squared is 0, which is this one, and where cosine is 1, this one. You add 1 plus 0, straight math, and you get 1, which says true to this equation. So what I'm going to do is the next point, and so basically that's roughly 0.09 for the sine, and this one here for the cosine is 0.95, and so both of those added together is 1.04. So clearly that is not 1, so this says this is not correct for this point in the sine wave. It is not 1. So you can say, okay, it is true sometimes, but not all the time. So let's just go ahead and step through it, see where it is true and where it's not true. The first quarter time, it's true at the beginning and at the first quarter. So it's 0 here, and the sine is 1. Okay. And I'm looking at my numbers, and it's showing extremely close to 0 number, which is actually registering on my slide as 0, which probably has something to do with the function and how it works inside of Excel. So this effectively, this is a 0, and that is a 1, and it's showing that on this particular document. So let's go another quarter term, which puts us halfway around. And so you can see how this, and this is my y, if you will, or the 1 in this equation, or the y in the same equation. So it's showing you it's such 1 here and it's such 1 here. Now it's going down actually to a -1. And effectively this 3.21e is right on the 0 line, because the e is the minus 31, so really close to 0. So I'm liking it. So let me finish it out. Let me finish the full loop of this. So as I said, pi is a halfway, and 2 pi is all the way around. So we should, yes, we cross it here. Once again at the starting point of is that the starting point? Yeah, at the starting point of the third quarter, and this is the point of start or the point of finish, the full circle around. So this is a complete loop, kind of like the diagram, the design. It shows you how the formula looks in a lined, pointed world, if you will. And then it shows you what the intersection or the combining or the addition of these two waves would look like. So that's one loop. That's a pretty picture. Let's see what it looks like for all of them. Like math. Like the pictures and the designs that it makes. Here it is here. Now I did mention earlier I wanted to show it to you by using another type of plot area, and I right mouse clicked on the table itself, and it gives me an option, change the chart type. So I'll do that. Come down to scatter plot. Yep, it's selected already because that's the one I took in. And oh, it looks like I've already made that change. Here's the straight line one. And go back. And this is the curved line one. So you can see how easy it is to change between, or even get ridiculous about it, which I will right now. And although that won't help anybody, let's just do this separate without the lines. Wow, almost looks like a smiley face. Let me put my lines back in there because that's what I wanted to show you. So grafting and points, they do make a difference of telling your story. So that shows me my problem 2 of sine x squared plus cosine x equals 1. And I say it's conditional, which means it's not in every case. And I could carry this, and I actually did. The loop would never stop, obviously. You can continue it infinitum, and it would just keep repeating this same pattern with this loop over this. And if I got rid of all of these here and just made this the formula of the function, which I could by doing this, just keeping my data points by doing that, and deleting the other stuff. It just leaves the green. So that's what the combining of those two waves actually looks like. Enough said. Like it.